Hello everyone. In this lecture, I will discuss heat treatment of titanium 6 aluminum 4 vanadium parts produced by selective laser melting. This alloy is also known as Ti6-4, is one of the most important materials used in aerospace and medical industry. Selective laser melting is also a very important additive manufacturing technique used to produce metallic parts. However, the parts produced by selective laser melting contain residual stresses, and it is important to relieve the stresses by doing the heat treatment. But this heat treatment can be used not only to relieve the stresses but also can modify the microstructure and has influence on the mechanical properties. In this lecture, first I will discuss some basics of titanium alloys, effect of alloying elements on its microstructure, and then I will discuss the heat treatments which are applied for the Ti6-4 parts produced by conventional methods, and then I will discuss the microstructure of as-built parts, and then I will discuss the investigations up till now performed on the heat treatment of Ti6-4. Pure titanium melts at 1670 centigrade. At room temperature, pure titanium exists in the form of hexagonal closed packed phase, also known as alpha phase, above 882.5 centigrades to 1670 centigrade. Pure titanium exists in the form of body-centered cubic phase, also known as beta phase. Alloying elements which stabilize the alpha phase of pure titanium are called alpha stabilizers, and the alloying elements which stabilize the beta phase are called beta stabilizers. Aluminium, oxygen, nitrogen, and carbon are the main alpha stabilizers used in titanium alloys, whereas vanadium, molybdenum, niobium are the main beta stabilizing elements used in titanium alloys. Based on the alloying addition, or based on the final phases we achieve in titanium based alloys, titanium alloys can be categorized into alpha alloys, near alpha alloys, alpha plus beta alloys, metastable beta alloys, beta alloys. Ti6-4 comes under the category of alpha plus beta alloys. So the final microstructure of Ti6-4 is alpha plus beta. Ti6-4 is one of the mostly used titanium alloys, and up to 50 to 60% of all titanium alloys is Ti6-4. It shows exceptionally good balance of strength, ductility, fatigue, and fracture properties, but can only be used up to 300 centigrade because of low creep performance. This alloy is heat treatable. At 800 centigrade, beta is 15%, and at room temperature, alpha is the dominating phase. Another important temperature for beta for Ti6-4 is beta transverse temperature, and it is 995 centigrade. Above 995 centigrade, it exists only in the form of beta phase. Aluminium is added to increase the strength of the alloy by solid solution hardening and alpha phase stabilization, whereas vanadium stabilizes the beta phase, which improves the room temperature ductility by providing the right balance by the presence of both alpha and beta phase. Like other beta stabilizers, vanadium can retard the formation of alpha phase and promotes the phase transformation of beta into martensite or the retained beta phase. When Ti6-4 cooled from the temperatures above the beta transist temperature, I mean above 1000 centigrade, when Ti6-4 is cooled, it can transform either into alpha phase or martensite phase depending on the cooling rate. Beta to alpha transformation occurs under the moderate cooling rates. This transformation is a diffusion control transformation and occurs by nucleation and growth of alpha phase on the extent of beta. During cooling through alpha to beta region, alpha nucleates at the grain boundaries. Grain boundaries or a high energy or in a higher energy state compared to the grain itself and provides nucleation sites. Further cooling leads to growth of alpha plates into the beta region. Further cooling through the alpha beta region leads to homogeneous nucleation and growth of alpha phase in beta grains, leading to woven basket-like microstructure. When cooling rate is very high, beta can transform into martensitic phase. This kind of cooling rates are achieved by quenching in water or oil. Martensitic transformation is a diffusion-less or displacive transformation. Beta can be transformed into either acicular martensite or massive packet martensite. When cooling rate is very high, above 410 centigrade per second, beta transforms into acicular martensite. And when the cooling rates are between 20 to 410 centigrades per second, massive packet martensite is formed. Um, the figure on the left is an example of acicular martensite, and figure on the right is an example of massive martensite. At this slide, we will discuss two figures. Figure on the left is a continuous cooling phase diagram for Ti6-4, whereas figure on the right is a collection of micrographs of Ti6-4 alloy when Ti6-4 is cooled from beta transist temperature, from above beta transist temperature at different cooling rates. Now coming to the continuous cooling phase diagram, also known as CCT diagram, you can see time is shown on x-axis in logarithmic scale, whereas temperature is shown on y-axis. On this diagram, you can see three phase transformation regions. One is martensitic transformation region, one is beta to alpha transformation region, and one region in the middle is beta to alpha and martensite transformation region. Excuse me. When cooling rates are higher than 18 centigrade per second, the cooling curve always passes through the martensite transformation region. Martensitic transformation starts at 800 centigrade and completes at 700 centigrade. Further slowing of the cooling rate results in the passing of cooling curve through alpha and martensitic region, and the resulting microstructure of the Ti6-4 will be a combination of alpha and martensite. Further slowing down of the cooling rate will lead to the passing of the curve from beta to alpha transformation region. The resulting microstructure is always alpha plus beta. Further slowing down of cooling rate will result into the formation of alpha plus beta phase. So there will be always alpha plus beta phase as in the final microstructure. However, the the cooling rate has an effect on the final grain size or the final size of uh, the microstructure. When it is when the cooling rates are very slow, it then can cause the coarsening of alpha phase and also the coarsening of alpha colonies. Generally, four kind of heat treatments are applied to Ti6-4 parts: stress relieving and healing, solution treating and aging, and heart isostatic pressing. Before we go and discuss these heat treatments, it is very important to note that whenever Ti6-4 or titanium is heated above 420 centigrades, the heat treatment shall be performed under argon or vacuum. Vacuum is more preferable. It is because above 420 centigrade, 7 centigrade, solubility of oxygen into titanium increases, and it leads to the formation of an alpha case around the Ti6-4 alloy. This alpha case is brittle and can crack and provide crack initiation sites and can lead to the reduction in the fatigue life. Stress relieving is performed to relieve the residual stresses in the components, and it is generally performed between 540 to 650 centigrades, and time can vary between 0.5 to 1 hour. The residence time is dependent on the temperature, and it can decrease very sharply by increasing the temperature. The aim of stress relieving is to eliminate the residual stresses without making much changes into the microstructure. The second type of heat treatment of Ti6 components is annealing. This heat treatment is generally performed between 700 centigrade and 815 centigrade temperatures, and the residence time can vary from 1 to 2 hours. The components are cooled from this temperature in furnace to 600 centigrade, and from 600 centigrade the cooling is performed in air. Time, temperature, and cooling rate are selected to achieve a mixed alpha beta structure which is stable and provides ductility. Another type of heat treatment given to Ti6-4 components is solution treating and aging, which is also known as STA. The idea behind STA is to obtain maximum strength levels. This is achieved by obtaining high volume fractions of beta phase in final microstructure. STA is generally carried out in three steps. First is to heating the components just above or below the beta transist temperature. This helps in a higher beta phase partition. Then in the next step, those parts are quenched in oil or water to preserve the beta phase partition. The third step is the aging of the components for 4 to 8 hours at temperatures between 480 to 595 centigrades. This step will decompose the residual martensite and unstable beta phase, which is preserved by quenching, and this will effectively strengthen the material. When solution treatment, which is the first step of STA, when this is given by heating the temperature, by heating the parts just below the beta transist temperature, you get a high strength while you retain the adequate ductility. When the solution treatment temperature is higher than beta transist temperature, above the 1000 centigrade temperature, you can achieve the excellent strengths, while a significant loss in the ductility will also happen. At this slide, I'm going to discuss microstructure of as-built Ti6 4 parts. I will be referring mainly to the work from T. Villaro from Polyshapes and Material Center of Mines, Paris Tech, France, and Mr. Bev Rankin from Material Engineering Department, University of Leuven, Belgium. Figure on the top left shows the microstructure of as-built parts on higher magnification. This is actually a scanning electron image, a scanning electron microscope image. You can see the fine needles of martensite. So that confirms that as-built part, the microstructure of the as-built part consists of martensitic phase. Figure on the top right also um, shows very interesting aspect of microstructure on the lower magnification, and that is actually an optical microscope of the etched Ti6 4 cross section, and you can see columnar grains. These were beta grains before they transformed into martensite. So we have the as-built part contains columnar grains and also shows the martensitic structure. Uh, because of the columnar grains, you shall expect the anisotropy in the material mechanical properties, and because of martensite, which is actually um, stressed stressed phase, you shall expect high strength and high yield strength and high hardness from such a microstructure. This also shows that cooling rate during selective laser melting were quite high, and it did not allow to transform beta phase into alpha plus beta phase, and it transformed into uh, martensitic phase, which is a diffusionless phase. Now coming to the mechanical properties, as built parts show, as I said, high ultimate tensile strength around 1200 megapascal, and yield strength is around 1100 megapascal, which is quite high compared to the reference material, which shows ultimate tensile strength of 1000 megapascal and yield strength of 960 megapascal, which seems to be like a raft material. For the cost at TS64, you shall expect even lower tensile properties. Another very important point here is the ductility. As for the martensitic phase, which are brittle, and you have high strength, but the ductility is low. Another important mechanical property is the hardness. The as-built parts show quite high hardness, and its value is around hardness Vickers HV is around 400, which is again higher than the conventionally fabricated parts. Another important aspect or the property of the as-built parts is that the tensile properties are dependent on the build direction. Here, here on at the top, the figure on the bottom left, you can see that when the parts are built in a transverse direction, their strength, either it is ultimate tensile strength or it is yield strength, is high than when the parts are built in transverse direction and then pulled later. This is mainly because of the defects. When the parts are built in transverse direction, it's the chances are higher that you get a cluster of defects which are aligned normally to the tensile stresses, and it leads to the lower ductility. In other words, the parts are broken earlier. No, you can see you can have very high strength, and but the ductility is low for as build parts. So the question arises that if you um, so if you want to improve the ductility and the microstructure, you shall do the heat treatment. There is another important effect, or there is another important fact, that these materials are so the as-built parts also contain residual stresses, and these residual stresses have negative effect on the fatigue properties, and these residual stresses shall be eliminated to have better fatigue life. Residual stresses can also cause distortion or warping of the parts when you remove them from the build, especially when parts are of complex shape, of complex geometry. It's very likely that they will distort when you remove those parts from the build plate. So it is always recommended to do the stress relieving before you remove the parts from the build plate. So you have to do the heat treatment of as built parts either for the stress relieving or to improve the ductility, and it really depends on your application, and your specifications. What is what kind of final microstructure and mechanical properties you are aiming. So on the next slides, we will discuss effect of heat treatment parameters. The heat treatment parameters play a very important role. When I say heat treatment parameter, it means, excuse me, the heating rate, the dwelling time, the cooling rate, they all the environment, they all play a very important role in the microstructure and mechanical properties of the heat treated part. So let's go to the next slide to discuss the effect of each parameter on the microstructure. At this slide, I'm going to discuss the effect of solution treatment temperature on morphology of grains, of the resulting grains. This is the maximum temperature the parts will see during heat treatment before they start cooling. This is a very important temperature as it determines the amount of beta phase in the microstructure before the parts start cooling. However, in the context of the printed parts, a very interesting effect is observed. When the parts are heated above beta transist temperature, like here in the image shown on the right, on the top left, is an optical microscope image of the cross section of the part which was heated 50 centigrade above the beta transist temperature, I mean at 1050 centigrades. And you see that the columnar structure of the grains which was existed in the printed parts is transformed into the equiaxed grains. Whereas when the parts are heated below the beta transist temperature, you don't see that effect. You can see the image just below the first image I was discussing here, on the bottom left image. You see the columnar structure you can still see in the micrograph, and this part was heated 50 centigrade below the beta transist temperature. So heating above the beta transist temperature converts the equiaxed grains in the columnar grain structure into the equiaxed grain structure. This is a very similar effect as we see in the case of the recrystallization treatment, heat treatment for the severely deformed parts, where the defects or the deformation in the material provides a driving force to nucleate new grains on the severely deformed grain boundaries, and then these grains or this nucleus grows, and we have a very refined, fine microstructure, and which generally leads to improved mechanical properties like strength, yield strength, ultimate tensile strength, yield strength, and fatigue properties. However, in this case, we see the final alpha beta Clooney size is very coarse, and this actually leads to the decrease in yield strength and ultimate tensile strength. However, the anisotropy can be restored and the part will show much high ductility. So once you are designing the heat treatment of your parts, you shall remember that what are the target strengths and ductility or you having in you want to have in your parts. The next important parameter we are discussing is influence of residence time on high temperature or the solution treatment temperature. Uh, by increasing the residence time, uh, the size of alpha and beta phases increases, and it also increases the Clooney size. Figure on the left, in the first on the top left, you see a micrograph of the sample which is heated to 940 centigrade for 2 hours. So the residence time for this part is 2 hours at 940, and whereas the figure below is a micrograph of the part which is heated for 20 hours at 940 centigrade, and you can see the coarsening of the alpha plates, and also the beta phase is also coarser compared to the figure on the top. You can also see in the figure on the right. So the top figure is for the part which is heated at 1040 centigrade for 2 hours, and when the sample is heated for 20 hours, you can see in the micrograph or in the bottom right bottom that the size of the colony increases. So influence of increasing the residence time is that you see a grain so the increase in size of alpha and beta phases, and also the colony sizes, and this can have an influence on the yield strength and fatigue properties of the parts. The next important parameter is the cooling rate. uh, when the parts are heated from um, a solution treatment temperature in the range of say 850 centigrade, the effect of cooling rate is not very significant. But when the parts are heated up in the range of beta transist temperature, the cooling rate has a very profound effect on the final microstructure. Um, the higher cooling rate leads to the smaller colony size and finer spacing of alpha and beta, whereas the furnace cooling results in lamella alpha plus beta microstructure. um, Air cooling from those high solution temperatures can lead to the formation of alpha Widman statin or basket weave like structure, whereas quenching from these high temperatures can lead to the formation of martensitic structure, as we saw in the case of azalam. So, the cooling rate has a great impact when you are you are starting from high temperatures. I mean, when the uh, part is heated to high temperatures for solution treatment. After solution treatment at high temperature, parts are quenched and then heated again to higher temperature. This temperature is also, or this treatment is also called aging, and this temperature is called aging temperature. Aging temperature has a very important effect on the microstructure or the final microstructure. It determines that how much martensite is transformed into alpha plus beta phase, and how long you have to hold, how long should be the aging treatment to transform completely martensite into alpha plus beta phase. For example, at 800 centigrade, the lower the temperature, longer the aging time to transform martensite into alpha plus beta phase. For just to give an example, aging time of 2 hours is required at 800 centigrade to completely transform or decompose alpha into alpha plus beta phase. This aging temperature also has a great influence on the increase in the aging time. Aging temperature can also lead to the increase in um, um, alpha phase size. For example, the parts he treated given the aging treatment at 750 centigrade shows the alpha size of 1 micron, whereas 2.3 micron alpha size is observed for the parts given the aging treatment at 950 centigrade. Another very important effect is um, another interesting effect of aging temperature is that um, when the aging temperature is lower, you can increase the vanadium contents in the beta phase, as you can see from the figure, because of that beta transus is in the form of curve. So by decreasing the temperature, you actually increase the vanadium contents in the beta phase, and which actually stabilizes the beta phase and doesn't allow and increases the ductility and doesn't allow beta to transform again into a martensite during cooling. Now we are going to discuss the effect of the heat treatment on the mechanical properties of the components. So you can see the table um, based on the investigations of Villaro. He categorized the samples into as built, then the set of samples which was given was heated above beta transist temperature, another set which was heated below beta transist temperature, and then a low temperature treatment. And then he also gave the properties of as cost and raw of Ti6 samples. So you can see the strength of as build parts is ultimate tensile strength is quite high, which is 12.6 megapascal. It's lower when the parts are built in transverse direction, and even then it is quite high, around 1160 megapascal. When the parts are given high temperature supersolvus treatment as a solution treatment, the tensile strength decreases to 1000 megapascal for the longitudinally built parts, and to 950 for transversely produced parts or built parts. Whereas when the temperature was the solution treatment temperature was lower, to equal to below the beta transist temperature, the ultimate tensile strength was 1036, which was slightly higher than the part with the high, which was given the solution treatment above beta transist temperature, but still lower than the as fabricated parts. In the case of the parts which are given low temperature treatment, they show also quite similar tensile strength. And you can see the similar kind of effect is found on the yield strength. So by giving the high temperature supersolvus solution treatment, the yield strength decreases to 913 megapascal from 1137 megapascal for as-built parts. And when sub transes beta transes heat treatment is given, and the yield strength is slightly better than high temperature beta transes heat treatment, whereas for the sample which are for the low temperature heat treated samples, yield strength is even better, but still lower than the as built parts. When it comes to ductility, uh, you can see ductility is increased by the heat treatment, which is quite similar for all the parts, for all the heat treated parts. And it is very interesting that low temperature heat treatment is also giving quite comparable properties for the parts which are given solution treatment at beta transist temperature or beta subtransist temperature. The only difference I can see is that those low temperature treatments will the parts will have the anisotropy. They will also have they still have the columnar grain structure. So, but their mechanical properties are comparable to what we achieve for the beta transes solution treated samples or beta subtrans transes temperature. So, so if we generalize, we can say that by applying the heat treatment to as-built parts, um, we see the decrease in strength, ultimate tensile strength and yield strength, whereas an increase in ductility is observed. Mm, it is another important point to mention here is that the maximum ductility achieved for by Filaro is around 9.5%, whereas the Franken achieved the ductility of heat treated parts around 14%, which is higher than what achieved by Villaro. Um, the, the main reason for this kind of difference can be that the amount of defects present in the parts built by Villaro is maybe higher than the samples from Franken, and this highlights that okay, the heat treatment is important to improve the ductility and strength, but SLM parameters or the density or the amount of defects in the parts also plays an important role, especially when it comes to ductility. They don't have a bigger influence on strength and ultimate tensile strength and yield strength, but they have bigger influence on the ductility, and those defects also has a very huge impact on fatigue life of the parts, and also generally when you have the defects, that means your process is either not under control or your parameters are not good enough, and this kind of parts also show higher surface roughness. So generally when you see the defects in the parts, you also see the higher surface roughness, and that also leads to the poor ductility. So heat treatment is very important, and also your process parameters or the defects in the build parts are also very important. So you need to optimize both of them. At this slide, you can see a table which summarizes the work of Mr. Bay Vranken on the effect of heat treatment on the tensile properties. You can go through the whole table, but I will just highlight few points. The first point is that He also, Villaro, he also found that by giving the high temperature heat treatment to SLM parts, the ductility increases to 14%, whereas the strength decreases. The other very important point for me is that sample 2 and sample 7, they show the best combination of the properties, and they are given different heat treatments. Sample 2 was cooled at 850 centigrade for 2 hours, and followed by furnace cooling, whereas sample 7 was first solution treated at 940 centigrade, followed by air cooling, and then again aging treatment at 650 centigrade for 2 hours. So if you look, sample 2 is given a heat treatment which is easier and shorter and easy to adopt in the industry, whereas the heat treatment given to sample 7, which also gives very good properties, requires longer times and also special equipments which can allow the quenching of the parts. So, but in the end, you get the same properties. So, the point I want to highlight is that when you are designing the heat treatment process, you shall keep in mind what what are the target properties, and what is the possible ways and which are more industrially suitable. Hot isostatic pressing, also known as hipping, is also another heat treatment which is given to as element parts. So hard isostatic pressing is achieved by simultaneously heating the parts and isostatically pressing the parts. Um, the other treatments which are given under argon or in vacuum, this also results into the transformation of martensite to alpha and beta microstructure. However, the alpha sizes can be higher for hipped parts. This is generally because the hip furnaces are cooling very, very slowly, and you can see increase in grain sizes of alpha. The biggest advantage is of using hip is that you can eliminate the internal porosities, which will help to improve the fatigue life. But be careful, it cannot eliminate the open porosities or the surface porosities. So you will gain the improvement in the fatigue properties by eliminating those pores, but you shall be careful that by increasing the alpha plate size, you can also decrease the yield strength, and which also decreases the fatigue strength. So you shall see those effects. I think the biggest advantage in terms of fatigue properties will be that the scatter of the fatigue strength will be reduced because of the elimination of the prostheses. Another important concern while adopting hip for heat treatment is that hip furnaces are very expensive. Can be around 1 million euros, and this is actually comparable or even higher than the price of the printers itself. So you shall be investigating first that you really need the hipping treatment for your components or not, and you shall justify the business case for these kind of investments. Like for the implants, the fatigue properties are very critical, and their hipping is always advised. So this was all about on the topic of heat treatment of T64 parts from my side. I will, yeah, if you have any comments or questions, please write down in the comments. And yeah, I want to also mention that I'm looking to prepare lectures on the additive manufacturing of metals and ceramics, and I will upload those videos. So I hope this video and the future videos will help you. And yeah, please don't hesitate to write in comments if you have any questions and remarks. So see you then later in another video. Bye bye.